Andreas, thank you very much for the introduction. So, let's use the next 30 minutes speaking about PHY processing for small cell cooperative networks. And what I will just discuss shortly is some key concepts for the PHY processing for cooperative networks. Once again, we talk about functional splits, but mainly focusing on the physical layer. And in contrast to what Andreas already talked about in his talk, I will give some details about, for example, also how to come up with the corresponding backhaul rates which are required. And we will discuss this with a kind of an example. Then I will discuss two possibilities for joint detection, so for uplink approaches in dense deployed systems, which is multipoint turbo detection and network processing. And then finally some summary. So in this picture, which Peter should have explained, but I think he dropped this slide, is basically the iJOIN architecture, where we have these small cells, which we call iJOIN small cells, ISCs, and we have here the cloud platform, which is the runners, and now we have different backhaul connections. We have the backhaul connection, which we call J1 interface, between the radio access point, or these iJOIN small cells, and the centralized unit, and we have the so-called J2 interface, which is somehow the connection between the different iJOIN small cells. So J1 and J2 are the different backhaul or X halls that we are talking about. And now the iJOIN concept asks for new algorithms in order to allow for a flexible centralization in this runners platform, and it asks for novel algorithms which allow this flexible cooperation and centralization in this overall architecture, where we will need basically joint detection schemes for the uplink transmission, some examples I will talk about later, and joint transmission schemes for the downlink, which I will not talk about here today because of lack of time. And for all these different techniques, we can discuss different functional split options, as we have already heard several times now today. Here we will address the corresponding physical layer techniques. In addition, the second pillar of iJOIN is the joint design and optimization of RAN and backhaul, where we in particular investigate the key properties of both links and identify the corresponding bottlenecks, and basically also which leads us to a joint design of both the links. And for this, Jens is giving also demonstration outside for this joint RAN and fronthaul coding demo, which you are heavily invited to visit. Okay, so what kind of techniques can we do when we have a distributed radio access network architecture? We can perform some kind of processing for this cooperative networks. Here we see the block diagram for some small cells, the RFAD converters, then FFT, the resource demapper, the detection, the decoding, then some MAC layer approaches, radio link control, and so far. And now different possibilities exist with respect to where to place the corresponding functions, what kind of requirements we have for the J1 and the J2 links, and what kind of performance gains can be achieved. We can, for example, just perform local processing in the ISCs, which means usually not that good performance, but no J2 communication at all, and a relatively low J1 communication because we just have to forward the estimated user messages. Another possibility would be to make a distributed processing among the ISCs. Now we have established a link between the ISCs in order to cooperatively detect the transmitted signals in the uplink, for example. However, this also requires then a J2 interface and corresponding backhaul rate. Hopefully we can achieve a performance which is kind of improved compared to the local processing. A third option would be centralized processing, CRAN, where we basically transmit all the IQ signals, where we, here in this example, we for example have part of the detection in the ISCs and part of the detection or uplink processing in the runners, which means we have a significant J1 overhead, hopefully also very good performance. We can maybe improve the performance by the CRAN approach, but this even requires more J1 overhead, or J1 communication in order to forward all the IQ signals from the ISCs to the runners. And finally, we have a kind of a hybrid local and distributed or centralized processing, which somehow can be maybe placed in this figure here. Good performance and then somehow kind of a flexible J1 and J2 overhead. In order to realize these different approaches, this will be very much depend on what kind of backhaul topology is available and what kind of functionality is really required in order to serve all the users currently with the corresponding quality of service. And this asks for this flexible functional split by this Ranas approach. In order to decide now the functional split, we have, for example, to take into account the computational needs in the ISCs, but also in the Ranas. We have to discuss the relative quality of the access and the backhaul link. So not only assuming perfect backhaul links, but also noisy backhaul links. We have to consider the deployment of the Ranas and the ISCs configuration. We should, of course, somehow have a kind of a disruptive extension of 3GPP. For example, HARC will always play a very important role when we talk about latency. And of course, the backhaul topologies, this J1 and this J2 capabilities, not only with respect to the rate, but also with respect to the latency, energy consumption, and all that stuff. And for this computational need, we also have a demo outside, which is the LTE decoder demo, which shows you what kind of challenges we also address when we implement now, for example, the decoder on a cloud platform, how this scales, or how this is computational resources scales with, for example, the numbers of users or the corresponding data rate. Okay, so let's talk about functional splits, and I told you already, let's keep it simple. I will discuss basically one example. For this picture, which we have already seen, Andreas introduced splits A up to D. The splits which are mainly concerned for the physical layer is, of course, split A, split B, and split C. Now let's have a look a little bit more detail to this different splits. We will introduce some kind of subsplits in order to then identify the most promising splits for the options depicted here. And as a kind of a school, let's do kind of an example. We discussed this common LTE uplink scenario, uplink processing chain. I have already talked about the RFID conversion, the removing of the cyclic prefix and the FFT, then the resource demapping, the receive processing, some kind of soft demodulation, and some kind of decoding. And basically, these options basically go back to split option A, split option B, and this is split option C, and everything on the left is processed locally in the ISCs. Everything on the right is processed in the central processing unit called Ranas in iJOIN. And let's talk about an example, an LTE uplink, 10 megahertz, 2 × 2 MIMO, 1 users only served, which uses nevertheless 25 out of the 50 available physical resource blocks. The numbers that you can see here on the right-hand side. So the first possibility is we are forwarding the time domain received signals. The IQ signals are quantized. So we have here, this is the throughput which is required. We have 2 for the in-phase and for the credit component. Then for each received signal, of course, we have to transmit the corresponding signals. Then, depending on the quantization level that we are using, here we are, for example, using for this split option 15 bits per I and Q component. The oversampling factor, which is for simplicity assumed here to be 1. And then we are forwarding the overall received signal in time domain, which means that the length for each subframe is given by the FFT size plus the cyclic prefix length. And then it depends, the rate depends on how many symbols are transmitted. So which leads for this very simple example to a fixed rate, a static backhaul rate of 920 megabits per second. Another possibility would be to go first into the frequency, to remove the cyclic prefix, and then to go into frequency domain. Why? Because then for the frequency component signals, we may reduce, first of all, the numbers of quantization bits, here, for example, now to 9 bits. And we are throwing away all these signals which are not really serving as payload, so the cyclic prefix and all that stuff. So basically here only the numbers of allocated subcarriers, which is here just 600, is transmitted, and all these signals have to be forwarded then from the ISCs to the Ranas, leading to a reduction by a factor of roughly 3 compared to the time domain IQ forwarding. So, and furthermore, it is kind of good to have an efficient implementation of the FFT in the ISC, which is nice from the perspective that when we talk about centralization, we really talk about cloud implementation on commodity hardware, which is a little bit more complicated to implement an FFT on a commodity hardware in comparison to specific hardware like we have deployed it in the ISCs. Okay, the third option for functional split A is we have a lot of signals here which do not actually carry any useful information for the users, which are not allocated by the user, this one user, for example, served by this ISC. And now if we, for example, assume that here we have now the corresponding payload, where we just transmit those received signals on physical resource blocks which are really allocated by users served by this small cell. And now in this example, I just assume that we have one user, and this one user just allocates 300 subcarriers out of the 600 available subcarriers. Now, once again, leading to a degradation by a factor of 2 of the required backhaul load. Of course, this is just a numerical example, and when you can play now with the different parameters, you will achieve different results. Now, all these functional split options A, the time domain, the frequency domain, as well as this payload forwarding, allow all the same kind of centralized processing in the runners, which means they all allow the same kind of centralization gains, which is of course nice. And they share at least roughly the same backhaul latency requirements. At least roughly, we will come to this later once again. However, from the efficiency perspective, of course, this functional split A3, where I just forward the signals which are really useful in order to detect the users in my cell, should be forwarded, and this should be really preferred from among these different sub-options. When we talk about functional split B, so then we have some kind of receive processing. For example, we perform an equalization of the users. Yeah. Then we are forwarding the filter output signals after IDFT once again to the runners, which now means that we can manage that the message size now depends really on the numbers also of transmitted layers, and we can nevertheless still use some kind of centralized processing, for example, centralized decoding. So we may use some kind of centralization gains, not all of the centralization gains, but at least some of them. Now here you see once again the example, and now once again we are achieving exactly the same rate as on the functional split A3. Why? Because here the numbers of spatial layers is exactly corresponding to the numbers of receive antennas. So in this time we don't have any differentiation, and also we kept the quantization levels the same. Now the possibility is we also perform soft demodulation. So here we are directly transmitting IQ signals. We may also use soft bits to be forwarded over the backhaul links. Now it of course depends very much on the quantization levels, but also on the used modulation scheme. And here, for example, for 64 QAM, QM, also the numbers of bits per transmitted signal, is equal to 6. And correspondingly, we have even here an increase in the backhaul rate. But this is of course an extreme case. Usually when we have just QPSK 16 QAM, then the numbers is 2 or 3 and correspondingly much lower. Okay, so these also are, this is also forwarding IQ signals or soft bits. And finally, we have the possibility to perform all the physical layer processing in the ISCs, which means we also perform FEC decoding and then transmit just the hard estimated information bits or the messages from the ISCs to the runners. And then basically the throughput depends on the transport block size. And here we are using we are assuming that both code words are allocated, so transport block size 1 and 2 add up, leading to a dramatic decrease in the throughput or backhaul requirement to 36 megabit per second. Of course, this is a minimum backhaul requirement because we put all the processing into the ISCs. Unfortunately, it also terminates basically the overall PHY processing in the ISCs, which makes it not possible for any joint PHY processing anymore. Nevertheless, it can be a good option if The ISCs are relatively well separated, for example, in an office building where we have different floors and we don't have so much interference. When we have a lot of interference and we would like to use or reuse the spectrum again and again, then this is not really a good option, at least from a processing perspective, in order to get centralization gains. This brings me to this intermediate summary where we have compared all the different functional split options, A1 up to C. We see that we have a strong decrease in the backhaul bandwidth. You will see here that the numbers are a little bit higher than the numbers I showed you before, because here we also include then the backhaul line code, which you always have to assume. The calculations on the previous pages were just for simplicity. We neglected this impact, and this also, of course, depends on the used line code. So between 1.2 gigabit per second up to 50 megabit per second. What we can also observe is that here basically functional split A3, B1 both, we have basically here in this example the same rate. Here we have fully centralized PHY processing. Here we have only some part of PHY processing, which is we can perform in a centralized way. So we have less gains. For example, no coding equalization is possible. Here we already see that we have a decreased requirement on the latency. So 3 or 4 millisecond HARC. So we have basically 3 milliseconds to operate the overall receive processing. For this here, CIPRI, this is using 5 microseconds. This is a requirement by CIPRI standard, which can be relaxed at least slightly when we talk about uplink and downlink transmission, that we, for example, here have a constraint with respect to the channel knowledge or channel aging, because then also we have to forward corresponding radio resource managements for the uplink and for the downlink and vice versa. And finally, we have here this option C, which is then where we basically perform all the processing in the ISCs and have just upper layer processing executed centralized. The one figure is really the bandwidth. The other figure is the latency, which is really, I would say, even the more critical point, because we are restricted by physics. We are restricted by the protocol, which is nothing we can really change that quickly. The rate we can try to extend by better and better techniques, leading to this picture which we have already seen in the presentation by Andreas. So here we have functional split A, where we have a kind of a throughput, and we have here kind of a latency constraint, and fiber, dark fiber, for example, is the technique which we basically need to do. To some extent also PON would be a possibility. Functional split B, here it depends, for example, millimeter wave, microwave techniques can play a very important role here already. Functional split C, latency requirement is even decreased. Also the throughput is decreased, and we may use more and more backhaul techniques in order to support such functional split options. And then finally, functional split D, which is of course not of the main interest of the physical layer processing. This concludes already the first part of my talk, and in the second part I would like to talk about some kind of joint detection techniques, so really physical layer processing in this distributed environment. And this is basically what we are dealing with. We know that we have several ISCs in the vicinity of a user, and of course it would be good to make first of all reuse of the physical resources, but also to perform joint processing of the users in order to achieve the highest throughput for these users in the area. So in the uplink, this means that techniques for joint multi-user detection would really be required in order to increase the overall area's throughput. And here we have the corresponding figure with the ISCs with several users which are observed by several small cells. And now we have the different links, the J1 link, the J2 link, and here are the radio access links. And in the next, I will just give you 2 examples of techniques that we have investigated in work package 2, which is multipoint turbo detection and in-network processing. Multipoint turbo detection follows a fully centralized approach, which means that we are looking for functional split A, where IQ signals are forwarded from the ISCs to the runners. However, in the runners and over the J1 interface, so we need a relatively huge bandwidth on the J1, And in the runners, then we perform enhanced turbo detection or turbo decoding block diagram, as you can see it here. So it's not just the common linear MMSE detection scheme, which is usually used, but it's really kind of a turbo detection approach, iterative turbo detection approach, and leads to these performance results for a system where we just have 2 users, 1 transmit antenna. We have 2 ISCs with 2 receive antennas, and we have a kind of a symmetric setup, so the users have basically the same average path loss to both of the ISCs, which is the worst case when we would really like to separate these 2 user signals. And here we are having frame error rates for LTE compliant MCS, and for example the red one, this is SQPSK with this parameter setup, and here we see the corresponding baseline approach, which is just the enhanced LMMSE interference rejection and combining technique, and we can see that by allowing at maximum 4 retransmissions in case of incremental redundancy, we can achieve a performance improvement which is significant in this area, and we can see basically the same also for 16 and 64 QAM. So what we can really observe is here that multipoint turbo detection, so basically centralized processing, yes, we were almost sure that this achieves some gains compared to local processing, but of course also we have to see how it exactly scales, how it exactly also scales with this implementation constraints, and here we have corresponding implementations constraints and see roughly a 5 dB gain at a frame error rate of 0.01, and we could even achieve larger gains when we achieve more HARC retransmissions. Another approach that we basically investigate here in our department is in-network processing, and let me just try to motivate this a little bit in more detail. So we have basically a kind of a joint multi-user detection, and we will see on the next page we can write down a kind of a centralized detection problem. The idea of in-network processing is to decompose the joint detection problem into a set of local detection problems, and then have a kind of an iterative processing among the ISCs, which means we are exchanging information between the ISCs, which leads to I would say, relatively high J2 overhead. However, what we can achieve is a performance which is close to the centralized performance with very low J1 overhead. What we basically achieve is that all this overhead, the backhaul overhead, occurs basically where also the signals occur, in the vicinity of the ISCs or between the ISCs, and not with respect to the runners, which maybe is deployed several kilometers away, depending on the deployment configuration. So what we can basically do is, or what we could do is, we could once again use the C-run approach, directly take the IQ signals, forward them to the central processing node, and if this is a received signal at one ISC containing all the transmit signals from all the users over all the transmit antennas, and then this is the corresponding channel matrix for one subcarrier of all the units to the ISC1, for example, then we can write this simplified system equation. And if we now collect all the received signals, Y1 up to Yj, denoting all the ISCs, we can also write down this kind of an overall MIMO system equation, which we can, for example, then use linear, nonlinear detection techniques in the centralized node. Let's, for example, use the least squares problem. So what we are looking for the estimated transmit signal, which minimizes this distance. The drawback of this approach is, of course, we have a one single point of failure. So if the central node corrupts or is broken, then we have, of course, somehow a problem. And also we have a strong requirement with respect to the J1 links, the connections from the ISCs to the runners, which also may cover several kilometers, so over long distance. The approach that we are tackling is that we are decomposing the centralized optimization problem into a set of problems per ISC, and then we are introducing a kind of coupling constraint, achieving that the estimates in the different ISCs for the users become, with the iterations increase, more and more the same. Yeah, we are introducing this coupling constraint. Nevertheless, we are solving basically this problem at every place based on the local observations only. This leads then to this iterative distributed optimization algorithm, detection algorithm, where we have to forward different variables between the ISCs. For more details, you can have a look to the corresponding papers and also, of course, to the documents of iJOIN. Leads to a significant overhead. Nevertheless, this overhead is just caused among or between the ISCs. The other benefit is that this technique is self-adjusting to the corresponding backhaul topology. So you don't have to change anything, but the algorithm itself, it knows how many neighbors are connected with me, and then you can share the corresponding information exactly with the corresponding neighboring ISCs. I already told you this has a significant overhead. We have nevertheless also developed several techniques in order to reduce this overhead, just named here 3 of them. But for simplicity, I will just have in our performance investigation with respect to this, I would say, original DICE approach, this distributed consensus-based estimation approach. And for the other algorithms, you may have a look to the corresponding papers. And in order to visualize the corresponding performance gains, we have investigated this wide area scenario where we have 7 ISCs connected with each other. Here we have the corresponding J2 links which are used for this distributed processing. In total, we have 19 cells. These cells, nevertheless, the users in these cells only produce interference that are not covered by this DICE approach. These small cells have a distance of 50 meters, and we have 2 antennas at each ISC and 1 antenna at each user. And this leads then to these corresponding area throughput gains for this given geometrical scenario. Here we see for LTE MCS between 1 and 9, so all the different MCS here are used. And we are assuming that all the users use all the physical resource blocks, so we have strong interference between the different users of the users in one cell, but also among the cells. And here we have the average bit error rate after just 5 iterations of this DICE approach. Here we see the corresponding results for just local observations, and here the area throughput saturates because of the strong interference, which are not covered really by this local estimation process, of course. In contrast, the centralized solution, which you can see here, achieves very good performance, for sure, because he can make use of all the received signals in a perfect way, and then can perform joint multi-user detection. And in contrast to this is our DICE approach. Oh, sorry, this should be green here. Okay, this is our DICE approach, and what we can see is, after 5 iterations, we are close to the optimum performance of the centralized solution, which serves as a baseline. And nevertheless, we could even close this gap by allowing for more iterations, but of course this leads more latency, more delay, and this is of course not beneficial. But nevertheless, what we can conclude is that this in-network processing approach, or this DICE algorithm as one of the implementations, is one very good candidate for this distributed joint reception. We will have a significant overhead between the ISCs. Nevertheless, we have already some techniques in order to reduce this also significant. But nevertheless, keep in mind that, for example, between the ISCs, maybe in the future we have millimeter wavelengths. But we don't need this fiber to the runners, which is maybe placed several kilometers away. And this brings me already to the conclusion, or to the summary. What we have seen, or what I have talked about, is we need, first of all, a kind of flexible techniques in order to allow for cooperation among ISCs in the runners. We discussed some preferred functional split options. I named them here once again. We see, nevertheless, that the backhaul or the data rate is the one term. The other term is really the latency. Nevertheless, in order to overcome also these restrictions of the LTE requirement with respect to latency, also, for example, opportunistic HARC can be used, or other techniques which achieves the same basically the throughput gains, but relax the corresponding latency latency we need for this new distributed or dense deployment of small cells, we need novel PHY algorithms for joint detection, for joint transmission. I talked just about two alternatives, one for the centralized, other for the relatively distributed approach. Of course, there are many, many more details to be discussed. Numbers of quantization bits are really sufficient, or what kind of quantizers are used, what kind of information needs to be exchanged, how does an imperfect backhaul sacrifice the overall performance. Many of these questions are already tackled by iJOIN in our work package. Some other questions can be maybe tackled in the future in upcoming projects. Okay.
Thank you very much. Very comprehensive overview of the PHY, and I think your last line actually is a very good point here. So I expect many more detailed questions, for example, from Mr. Haberland and also from other participants.
But kind of when we have this dice concept, what kind of latency requirement you have then among your access points?
This is of course, we need to meet at the end the 3-4 millisecond HARC requirement. And of course, it's a little bit difficult for us to bring this directly into kind of an implementation, to really see later on the implementation, what kind of latency is really then occurred by the processing. No. We don't need a complete mesh network. You can also, for example, in this example, these two ISCs don't talk to each other. Yeah, so this is.
But when you want to apply it for the general case, where users can be, because you can build a subclass, you can have a lot of different subclasses.
Yes. And this you can basically manage based on the current user. So are the users then placed on the same physical resource blocks or not? And then you can set up this dense explanation was, here we basically have some kind of neighborhood relations. And this is basically what the radio resource management also can somehow give us. In combination with the radio resource management on the RAN for the users, then we can also let exactly the right ISCs cooperate with each other. And therefore, we can, of course, also decrease significantly the overhead. What I assumed for this here is basically just these corresponding connections. But of course, this leads to a lot of challenges also of how much cooperation do I really need, because I have to pay for it. On the other hand, it achieves or leads to very good performance in order to also achieve basically centralized performance, but with just localized backhaul traffic. And this is, I think, really the benefit. And this kind of flexibility with respect to the different scenarios. So it's self-adjusting.
Maybe can you elaborate a little bit more on which kind of when you realize this, at which split point you would then split concerning the one?
You mean functional split?
Yeah.
This is functional split B or C. But basically, this is functional split B. So we have basically processing. We have kind of receive processing. In this picture, when we talk about functional split, we only talk about ISC to RANers communication. But we, of course, also have, when we go some slides back, we, of course, also have this communication. Nevertheless, the rates which are required for this split are basically a factor of the corresponding functional split option. So here we are exchanging IQ signals among the ISCs. Correspondingly, the functional split, or the rate here will scale with this functional split option B. Like equalized transmit signals are basically exchanged. Of course, when you talk then about iterations, then you talk about several signals that have to be exchanged. Of course, this will cause traffic.
The
memory requirement is not that So basically what you see here is that the functionality is very, very simple. The updates just, they are really very simple calculations, no complicated algorithmic to do.
Can you quickly interrupt here?
Yep.
It's a very interesting conversation, but I think we have some other questions. I think Ralph, you have.
So let's assume we do this split as you propose. How forward compatible is this? So this is now based on LTE OFDM. So let's say for 5G there are lots of different flavors ideas around for modulation schemes. And if we look for a particular interface, then it's very difficult if we then not really forward compatible in a way that we can't reuse.
Can you write it down in such an equation?
Those schemes look at cyclic prefix and without and circular and not and so on. So it's a bit more complex, I would say. In principle, it's still some linear transform of equations. But the detail is a bit more,
sure.
More complex.
Okay, so here also we started with this very general question of this optimization problem. And then later on we applied this to LTE. Yeah, so the framework is very general. Nevertheless, it can be applied for LTE. It can be applied also for some other structures. So I would say it's then of course the tricky things. Then you really have to investigate and they have to see where are really the problems at hand later on. But in general, as you can write it down as a kind of linear equation, at least for this approach that we have discussed here. So network processing is a more general framework, and this DICE is just one implementation in order to achieve this in a distributed way, a kind of a centralized solution.
And the other question would be, what happens if I go to, say, active antennas? Yeah? If I go to, if I have at a terminal 10 or 20 or 50 antenna elements.
Yeah.
At a base station, that's okay, but also in a terminal, if you think a terminal is a car, for instance, then this is would be a feasible thing. So how would this operating point where you have one solution is better than the other would probably fit? Have you thought about this?
No, not actually. So of course, all these problems scales in the numbers of antennas. When you talk about the numbers of receive antennas, that's great, yeah, because the numbers of received signals are not exchanged at all. We are basically exchange transmit information. So estimated transmit signals or hypotheses for the transmit signals. These have to be exchanged, but not the received signals. And then it leads even to a better conditioned, I would say, a linear equation system. And then you can maybe use less iterations in order to come to the good performance. But once again, this is something, when you exactly then have the problem on the table, then you can design it exactly how that it fits also this problem. But we haven't investigated this because for us currently the LTE scenario was the one that we would like to address for our evaluations.
Thanks a lot, Dirk. I guess we have to move on. We are
Coffee.
over time. So thanks again.